Good morning. How are you doing, Nick? It's fair. Yeah. I'm a little tired as well. That was a cool video, though. I think all the proofs of Brouwer's fixed-point theorem are cool. It's just a cool theorem. And the pi thing was very relevant. Yeah. Yeah, I mean, these other metrics definitely can be super useful. Yeah, it's all about, like, we just kind of chose the straight line distance because that's, like, what makes sense, but you can definitely choose other ones. Morning, Will. Did a combinatorial proof for grad sim last year. Ooh, that's spicy. By the way, Mark, while you're at it, if you want something fun to do, which may or may not actually be fun, can you actually describe all 12 elements of this group? This is the dicyclic group, but this is like a different presentation. Yeah, I don't know if you have GAP installed. I didn't have time to do it this morning, but I want to draw the Cayley graph for this guy. I know at least 9 of the elements, but I don't know the last 3 yet. Like using ABC equals E gets you some of this stuff. Well, I mean, it's for more than fun. Well, for him it'd be for fun. For me it'd be for potentially trying to do our research problem for all groups of small order, at least order below 16. Also, I want to hear about that combinatorial proof afterward. That sounds cool. I don't know if I know that one. I'm not sure. Okay. Seems like... Oh, there's Rippy. Okay. Alright, so let us begin. So, like I said, we did 415 last time, kind of the roundabout way through the quotient. We had to verify that it was well defined. We had to look at our open sets there by translating them into open sets in the space above, because that's how the quotient space is defined, right? Our open sets are in terms of the open sets above. And that seemed like a pain. And so I said, let's have 217 and 218 and then see if we can redo it in maybe a faster way. And so, okay. So 217, I just want to prove these first so we have the tools, and maybe you at least believe them. So it's all about this diagram, right? So we start with, this is a quotient map over here. And then we've got some map G. And then the first thing that we really want to claim is that there exists some F here, right, such that G is F composed with P, right? And so the important thing for this to work is the assumption we make on G. So G has to be constant on equivalence classes. Okay, so G is constant on equivalence classes, i.e. if the class of X equals the class of Y, then G of X equals G of Y. Now, this statement will get a little bit stronger in 218 because here we're not talking about a homeomorphism. In fact, this does not make F into a bijection necessarily. So right here, all we're saying is that G is something satisfying this, and then we get f from x star to z by defining f of the class of x to be g of x. Right, so this is what I mean by inducing. No, so yeah, that was what I meant. So the if and only if x is equivalent to y is in the next statement. So here, you don't need it to define a map, you need it for this map to be injective. That's the important thing. So we can give an example of the difference. And the key here, right, f is well defined given this assumption on G. Right, because if you take any two different classes, well, that's just saying f of x equals g of x, but that is g of y, so if the classes are the same, then we get the same result, right? Because this implies this. Okay, so that's obviously the first step. And so we now have this function, we have this like triangular diagram, and again, this should look somewhat familiar, hopefully, right? You have something like, if you have a surjective map, maybe I'll draw this next one when we actually talk about the homeomorphism, because we can talk about the first isomorphism theorem. So then the two things that we want to show after this are f is continuous if and only if g is continuous, and f is a quotient map if and only if G is a quotient map. Okay, so I'll redraw the diagram here, because the key observation is just like how the open sets play around, right? So when is f continuous? Well, that's when, if you pull back an open set in Z to its pre-image in X star, that's got to be open, right? So f is continuous if and only if U open in Z implies f inverse of U is open in X star. Well, what does it mean for the pre-image to be open in X star? Well, that's completely defined in terms of its pre-image above, right? You have to travel back upstairs using the quotient map. So this is true if and only if, can you scroll up for just 1 second? Yeah, sure. I'm not sure what you needed exactly, but hopefully that covers it. Yeah, so this is true because P is a quotient map, right? So F inverse of U is open if and only if P inverse of F, right? The pre-image under P of the pre-image under F is open. So basically with the second statement being if and only if, you can say this whole implication is an if and only if. So U is open, I probably don't need to keep saying in Z. P inverse F inverse of U is open in X, since P is a quotient map. Right, so this is literally how we define our open sets in X star. Well, now we have this. We know what the pre-image, right, the composition of pre-images here is exactly the pre-image under G. And so we have U open implies the pre-image under G is open in X. And this is exactly G being continuous. Right, so it's all about, basically everything follows there from this being a quotient map over here, right? So that our open sets in X star are defined in terms of the open sets of X, and that helps us travel back up to where G begins, and then we can translate over to the other map. Does that make sense? I mean, this is, yeah, this start. Right, yeah. But yeah, fair point. If you are a quotient map, you are definitely continuous. Okay. So what does it mean to be a quotient map, right? So F is quotient if two things are satisfied, right? So F is a quotient map if and only if F is surjective and the condition on preimages holds, right? So, and U is open. Well, they're equivalent. So I'm just going to start with F, but yeah, you could do either. And U is open in Z if and only if F inverse of U is open in X star. So really, the second part here, this is exactly the same, right? Because you're basically going to be doing, okay, F is quotient, so you have this condition on open sets. Well, what is the second thing equivalent to? It's if the preimage under P of that set is open in X. Oh wow, we have the preimage of P of the preimage of F, so that is the preimage under G, and you do exactly the same steps as here basically. So this part is the same as above. Right, it relies upon P being a quotient map. So I'm not going to just go through that again. That is really pretty much the exact same thing. The question is, so why is F surjective? So then it boils down to why is F surjective if and only if G is surjective? Okay, so this is where it's important that G is F composed with P. So why is this true? Yeah. Do we know anything about compositions of maps being surjective or anything like that? So let's say I know G is surjective. So if G is surjective, then this means F composed with P is surjective. Do you know anything about composition is surjective? Does this imply like both of them have to be surjective, at least one of them, a certain one of them? I think you actually proved this during abstract last year. I think I made this like a random problem on a problem set. Do you see a picture in your mind when you see this? Yeah, so F definitely has to be, yeah, that's a good way to think of it. It's like the last step, so like if your last map doesn't hit everything, then the whole composition is not going to hit everything, right? But actually P does not have to be surjective, so you can just do this with like simple dots. So if I did something like this, right, so my F map is going to be surjective, and my P map will not be. Right, so this would be P, this would be F, so like I don't hit this guy here with P. So like P is not surjective, but F is surjective. And in general, yeah, the last one has to be, but the other one does not. Obviously, if they're both surjective, then you're good. Okay, so that gives us 1. So why is this true? So if F is surjective, why must G be surjective? So this is not true in general, right? So if you have a composition and the last one is surjective, you can't go back the other way. Again, think of another diagram where let's all go to one point here. Right, so like F is surjective, but the composition is not because you only hit this point over here, right? So it doesn't follow because that previous statement is if and only if, because it's not if and only if. So here there's something more going on. It seems like it maybe has to deal with our certain situation. So do we know anything about P in our case? It does have to do with kind of the equivalence classes, like it more, which kind of has to do with the map P. Here we know P is surjective, and so we do get it for free. So F composed with P is composition of surjective, and hence surjective. So this is specific to our situation where we know P is actually a surjection. But in general, the composition where F is surjective, if P wasn't there, then this would not necessarily be true. Okay, so that was this first proof, which basically is just getting some of the preliminaries out of the way and showing that you can do things with a little weaker statement. But then if we actually want a homeomorphism, we have to have a little bit stronger condition on G. So right here we just said it has to be constant on equivalence classes, but you could have, for instance, x goes to, let's do a specific example here. So this will still be just like a 1-point space, but you could do, you post these, right? I do. Let's just do R2 to R2 mod tilde, the one we had last time where you just like do the projection onto the y coordinate basically. So then this is definitely not going to be a homeomorphism, right? Because this guy is basically a line. I don't know why, whatever. This is like a line, and this is a point. These are not going to be homeomorphic, but this is constant on equivalence classes because, well, it sends every single point to the same point. So like this would work for 217. This would mean that this f is continuous, and if this is a quotient, then this would be a quotient, and this, yeah, is for free basically because it's the constant map. But this doesn't really tell us what we want because we want to show like homeomorphisms. And so the idea is we want something a little stronger. We don't want to just send equivalent things to the same thing. We want to only send equivalent things to the same thing, right? So if you send to the same thing, then you had to be equivalent. So for 218, our assumption is a little bit stronger. So here, we want same diagram, right? So x star, p, g, f, but here g of x equals g of y if and only if x is equivalent to y. And then we want g to be surjective and continuous. Okay. And so our whole goal here is to show F is a homeomorphism if and only if G is a quotient map. So we have several things here, and I guess, yeah, so first we're going to show that just these conditions here will imply, so I'll just say, star, okay, I'll actually do a star rather than an asterisk. So first we show these conditions star imply that F is a continuous bijection. And so, well, I mean, F is definitely induced, but yeah, that it specifically is a continuous bijection here. And most of this follows immediately from 217, right? So from 217, since G is continuous, well, first of all, since G is constant on equivalence classes, we get a map F, a well-defined map F. And then, since G is continuous and surjective, well, we just showed that those things were if and only if F is those things. F is continuous and surjective. So then what we're missing is that F is one-to-one, right? That's the only thing we need to show. And this is where we actually get this result from this additional, right? The fact that this is now if and only if and not just one way. So I think Nick last time kind of noted like, hey, this one-to-one and well-defined thing, these are basically the same thing except you're like going the other direction. Well, the thing that guaranteed us well-defined was if they're equivalent, then G is equal on them. And now this time we get the other direction too, and that's going to give us one-to-one. So, you know, suppose F of the class of X equals the class of Y. Well, by definition, this means G of X equals G of Y, and we know this then implies that the class of X equals the class of Y. Maybe I won't put that many so's. I'll care a little bit about sentence structure. Thus, F is one-to-one. Okay, so we get a one-to-one map, and this is where I want you to think back to group theory, right? So like if you have the same thing, if you have a surjection onto H, right, you have some homomorphism there that's surjective, well, then you can mod out by the kernel, which is always going to be normal, so like that's a legal maneuver. And then you'll get, right, this is going to be some projection map down onto your coset, right? Like the element X goes to the class of X, or, you know, X times kernel theta. And then it turns out, right, that phi of X being equal to phi of Y means that phi of X inverse Y is in the kernel, right, because X inverse Y, you would just like bring this over and then that would go to E. And this is true if and only if, right, X inverse Y is in the kernel, so this means X times the kernel is equal to Y times the kernel. And so that's exactly the statement that they have the same equivalence class, so the same coset. And then basically you mod out by the things that went to the same thing, so you glue all those together, and suddenly, instead of, you know, having like many things going to one to be one-to-one, we just say, well, turns out these are all the same thing, and then suddenly you just have this red dot goes down to the blue dot, and you're one-to-one. And so like this is the idea of what's going on. We're like gluing up the badness that makes it not one-to-one to force it to become one-to-one. So we've got a continuous bijection. Also, again, feel free to ask questions if you have them here. Okay, so then we want F as a homeomorphism if and only if G is quotient. Well, now that we know F is a bijection, so bijection, by 203, this reduces to, well, okay, so I'm going to do the one that makes my preimages a little bit easier. So since F is a bijection, F inverse is also a bijection. And then by 203, right, so 203 states, well, several things, but the one we want to use, so if you go back there, like all you needed was a bijection, didn't have to be continuous, so I'm not like claiming F inverse is continuous at this point, because that would be proving it already. So all I need then is, so first of all, where's F inverse coming from, right? So F inverse is going from Z back to X star, and so I would be taking F inverse, oh, yeah, no, I already said that. F inverse is a bijection, so F inverse is a homeomorphism if and only if for any open U in Z, or sorry, U is open in Z if and only if F inverse of U is open in X star. And this is where aren't those equivalent? Yeah, so I can use the preimage because then I can use the same argument as I did in 217. Right, so F inverse of U is open in X star. Right, so F inverse is a homeomorphism if and only if this, so we would have this is open in X star if and only if P inverse, F inverse of U is open in X, if and only if G inverse of U is open in X. And so essentially so what we really have here, right, is F inverse is a homeomorphism if and only if F is, and this would be true if and only if, so U open if and only if this, so it's like this statement, if and only if this, if and only if this, so we have U open if and only if G inverse of U is open. And so G is already surjective, so this would be if and only if G is quotient. So notice like this, P being a quotient map is like the key to everything in terms of the stuff with open sets working out. Questions? So the reason that I really wanted to prove this and then do some examples where we use this, I think this is like a challenging part of the class, and it's probably something that I like could decide to omit and be like satisfied with doing the product and the subspace and stuff, but like I think this is really important because of how ubiquitous quotients are in math. And why did I write that last part? Because that was the actual statement that I wanted, right? That F was a homeomorphism if and only if G was quotient. And G being a quotient map does have to be surjective, so it's more than just the statement on open sets. So I did have to like restate that, or I wanted to restate that. It was assumed from the beginning. That's part of the definition of quotient map. Right, your quotient if and only if you're surjective and satisfy this condition on open sets. Because I need G to be a quotient map. Like, it wasn't integral to any of these pieces, like, once F was a bijection, right, like, G being surjective was important up here. But, like, for this, I'm just kind of saying, like, this is true, so, like, it does satisfy the definition. No, I mean, it's our basic assumption in 218. We assume from the start that G is a surjective continuous map. You sound dissatisfied. Yeah, I mean, the open set condition, like, doesn't require surjectivity. What? Sorry, I missed that. Okay. All right, so let's go back and relook at 215, right? So 215, proofs on the fly are hard. That's true. Yeah. Yeah, I mean, that's why I suggest asking questions. I guess I tried to answer, but maybe it's just too hard with the delay. I'm not sure. Okay, so here we had the R2 mod tilde. We wanted to show it's homeomorphic to S1, and this relation, right, was that AB is equivalent to XY if and only if B equals Y. So what we would like to show is that we don't actually have to define a map from the quotient space at all. In fact, all we are required to do is show that we have, this continuous surjective map that is constant on equivalence classes, or well, equal on elements if and only if they're in the same equivalence class, right? So we want G such that G of X equals, well, that's dangerous. These are elements of R2, so let's just say G of AB equals G of XY if and only if AB is equivalent to XY, and G is surjective, well, G is quotient. That shows you everything. Oh, sorry, R. Yeah, I'm just not thinking at all. I would have figured it out. Yeah. Yeah. Yes, thanks, Jay. All right. So, yeah. I would have figured it out when I did my map and realized none of these were points on a circle. Okay, so this, I mean, sometimes you can just guess the map, right? But, like, you should be informed as to what the map should be here, right? So, like, we have G of AB equals g of xy if and only if AB is equivalent to xy. But what does this mean? Well, AB is equivalent to xy if and only if b is equal to y. Well, that kind of tells you what this should be, right? This should be b, this should be y. Basically, this should be my projection map, right? So define g of AB equal to b. And then this satisfies the condition on equivalence classes. Whatever, I'm just going to write star, the condition star. And so then we would like to show that this is quotient. So now so again, there are two pieces to this, right? So first, is G surjective? Well, that's clear, right? Yeah, we hit every real number because you can have any number be your y coordinate, right? So then your second condition, right, is that U is open in R if and only if its preimage is open in R2. So one of these ways is easy, but how do we show an if and only if here? Thoughts? You can also just say, like, which way is easy. Or hopefully is easy. Or anything at all. Left to right is easy, yeah. Yeah, so left to right is pretty easy, right? So if you have, and again, because of 27 for us, right, how unions of preimages versus preimage of unions works, kind of suffices to look at, say, some open interval from A to B. That's fine. Okay. AB as a subset of R, just to be clear, that is not an element in R2. Then, so if we have this, then G inverse, or the preimage of this point, what is its preimage going to look like? Yeah, sure. Yeah, that's a good way to say it, yeah. Yeah, so it's R cross AB. If you wanted to write it in terms of points, right, it's XY such that Y is in that interval from A to B. Same thing. And since X is allowed to be anything, yeah, and this is going to be open, right, because this is an open set, this is an open set, so we're good. So this is open. So the other way you can do a couple of things. So sometimes this isn't going to work, but here it would. So it suffices to show G is an open map. Why? Since G of G inverse of U is actually equal to U here due to G being surjective. So if you map open sets to open sets, then if G inverse of U is open, U is going to be open because G of G inverse of U literally is U here. But this is not required. It doesn't have to be an open map. Sometimes it's not going to be. I think we'll see an example with like the 0, 1 to S1 map. Like that one's not going to be open because of kind of the same issue we saw previously. But another way then to do that would be to think, okay, well, what if you're not open in R, right? Well, then you have some point in your set that's not in the interior, so basically you have some closed thing. It doesn't have to be on both sides. And then once you have a closed thing here, you're going to get a closed thing up above in your pre-image, right? You're going to get, instead of an open band, you would get, say, a half-closed band, and this is not open in R2. So like that would be kind of the contrapositive there. Yeah, just a second. So open map just means you map open sets to open sets. So G is open if whenever U is open, maybe I'll call it V since we already have a U here. V is open, G of V is open. And so I think, yeah, this is perfectly fine as an argument. If you want to show it's an open map, that's not too bad, because if you think of, oh, sorry. Yes. If, sorry, a continuous map, if it's surjective. What do you mean? Homeomorphism is so it's what, a continuous bijection such that the pre-image, as long as you have the bijection part, then it being a continuous open map is enough, because you have surjectivity. So like if that comes from the open mapness, right? So F inverse is continuous if whenever you have a V open, then the pre-image under this is open. But if this is a bijection, right? If F is a bijection, then this is equal to F itself, right? And so this is exactly F being an open map. So that's why the openness is nice. So that is giving you that the pre-image is continuous. And so here, right, if you wanted to show this, so to show this projection is open, well, take an open set here, right? You have G of AB cross CD, say. Well, this is just going to be the set CD, right? You're just projecting all this stuff over here, and all you get is this open interval. And so, yeah, it's going to be an open map. And again, it suffices to look on the basic opens there. So either one works. So the contrapositive up here or showing it's open, either one will show you kind of the other direction there, the right to left, and you would get a quotient map. Does that make sense? I'm not sure what way feels easier to you. Again, like it's not always going to be possible to show it's an open map. But yeah, how do you guys feel about using G and not really doing anything with F? Do you have no feelings? There should be a flow chart. That sounds like a fun project for you guys to do. I mean, all you have to show, it's really just like the different ways of showing the quotient, right? Which is really just like what, it all boils down to like one thing, because you're doing most of the stuff the same every time, right? So like g of x equals g of y if and only if x is equivalent to y. That's like always your step one. Step two, g is quotient, which basically boils down into two things, right? So A, G is surjective, which is usually obvious from your map, which comes from 1. So like this is almost never any work at all. And then your other part is the open sets condition, right? So that's the only part that really requires much work. And yeah, I mean, sometimes you just like straight up do it both ways. Maybe one using the contrapositive, it's usually easier. Or the one direction could be by showing an open map. But I don't think there needs to be like a massive flow chart. I think you're making it sound like it's more steps than it actually is. Or do you mean just like homeomorphisms in general and not like specific to this question? I don't know. All of the above. I mean, we have theorem 203. That tells you exactly when something is a homeomorphism. That was the whole point of that theorem. We have a bunch of equivalent conditions. And I mean, usually the one you'd use is, I mean, sometimes closed sets are easier, but we're pretty used to open sets. And so using the U is open if and only if f of U is open is your most consistent. Doesn't include this stuff. Yeah, so it's this plus that. Okay, so take away 3 and 4 and you have this and that. So it's one thing. Okay. So basically remove things from the previous and add one thing, and so it's actually like less than what we had in 203. Awesome. Alright, sounds like a fun flowchart. What do you mean some open system? Alright. Okay, so right, this quotient space, this was R2. Hold on, I need to remember what 179 was. Open map. That, yeah, but open map is just a definition. That is the condition in 203 that you use, right? That's one of those directions. So that's just knowing what open map means. That's not a condition that's like not stated there. Okay. Right, so this one is R2, and I'm just going to call it X because I don't want to continually have to write this. And then this goes down to X mod tilde, and again this is identify points on the same ray. New idea, reduced terminology. Open map is a very useful term. Would you like to say maps open sets to open sets every time? That's fine. You don't have to use it. I would know what you mean. So here, right, we identify all points along a ray from the origin. And by identify, I just mean like glue together, right? So glue together. That was our equivalence relation there. So I saw people approach this in a couple of different ways. So I think polar can be very useful here, but you also don't have to do it. You can still stay with your nice little Cartesian coordinates for sure. So we're going to S1, right? And the idea is we just like picked some point along these rays, just the one distance one away from the origin, and that was kind of arbitrary. We could have chosen any circle and make this work pretty easily in the same way. So yeah, I saw a couple of things. So I saw like g of xy. Well, how do you make it on the circle? So I think, Nick, this is what I saw from you. You kind of used what we did in, what, like 213? Something like that, where you just divide by the length, right? So you have like x over the square root of x squared plus y squared, and this makes sense because we're not at the origin, right? So we're never dividing by 0. And this ensures that you're on the circle, which is pretty cool. You could also do g of r theta is just 1 theta, right? You want to keep the same angle, but your distance 1 now. Either of these makes a lot of sense. For me, notationally, I guess this is just easier because I'm not writing square roots and stuff, but like it's the same map, right? Like, so either one works. Yeah, I did good. You did, yeah. Yeah, and I think that personally, I guess, yeah, it doesn't matter, right? It's personal taste, and for me personally, it was just like easier to write this, especially with the equivalence relation, because I don't, I'm really talking about the angle anyway, and so really you have like r theta is equivalent to r prime theta prime if and only if theta equals theta prime, right? And so our map respects this because g of r theta equals g of r prime theta prime if and only if 1 theta equals 1 theta prime if and only if theta equals theta prime. So you would get the condition on equivalence classes that you want. Again, clearly surjective, right? That's not a problem. So we get this, surjective, yes, for sure. And then you just have to think, okay, well, where do my open sets go, right? Like, what is my condition on open sets here? So you open in S1 if and only if the preimage is open in, I'm just going to call it X, right? That's why I introduced that notation. Okay, so thoughts here? So what do open sets look like over here? And then what do their preimages look like? Devin, I wrote about the issue with arctangent is that you don't get all of theta, right? Arctangent runs between negative pi over 2 and pi over 2. And so you're not able to distinguish antipodal points on the circle. So like xy versus negative x, negative y. You're not going to be able to see the difference between them. All right, Jack. It was an interesting idea, though. But yeah, that was kind of an issue I saw with a few things where we use like arc. What? I shouldn't hear you. Okay, but I just didn't hear. I mean, think about the graph of arctangent, right? Like you're only going from negative pi over 2 to pi over 2. So how are you going to get a whole circle's worth of things? No, it's defined for all values, but its output is not. Yeah. No, you're correct, but the issue is its range, not its domain. Its range is negative pi over 2 to pi over 2, so you're not going to be able to spit out angles. No, so like all the things that you map to, if you think of like polar coordinates, lie here. Right, like your map is going to take a point and it's going to map it somewhere here. Because the angle that it spits out in the y coordinate or your polar, whatever, your theta coordinate is always going to be over here. You're not going to be able to get this. Yeah. Yeah, so it's more the range and not its domain that's the issue, yeah. Right, so our open sets, right, like U is either the empty set, in which case, like, life's easy, right, or it's like a union of open arcs. Well, the pre-image of an open arc, so, right, it kind of, again, reduces to the case of an open arc, right, so an open arc can be thought of, right, the set of, like, 1 theta, where theta lies between a couple things, right, an open interval. And then so G inverse, so if this is U, then G inverse of U is an open sector, right? So this would be the set of all R theta, where you have the same restriction on theta. And so basically what you're doing, right, is you have some circle and then you actually get the whole thing, right? So you get all of this stuff in this open sector. And so like that's the easy direction again. And then right, like you could either think of where do open rectangles go, right? So like showing G as an open map, like where does this rectangle go? Where, well, it kind of depends on the cases, right? So if the rectangle contains the origin, then you get the whole circle, right? So if this is U, then G of U is S1, which is open. And then if it doesn't contain the circle, or sorry, contain the origin, then you're going to get exactly wherever this intersects, but intersects the circle, right? So then you would get exactly this open interval here. It'd be some open arc, right? So this is open. And then your last case would be that it doesn't matter. Never mind. It doesn't have to intersect the circle. I'm stupid. All right, yeah, we're projecting down or up, so this is fine. This is your other case. No, it wouldn't. Yeah, it doesn't have to intersect. Yeah. Yeah. Yep. Yeah. Yeah, so it's really just like wherever it maps. So maybe I can draw a better picture here. So I can probably make that happen. So let's just say we get this, and then you just look at all of these rays, right? And then it's this on the circle. So it's exactly this piece. Yeah. And so G is open either way, and so thus G is going to be quotient. And thus our F, which we didn't even talk about at all, is a homeomorphism. And again, this is nice because you don't have to talk about F. You don't have to worry about equivalence classes, right? So it's the same thing with group theory. Like, cosets are weird and people don't like to deal with them a lot. And so if you can just deal with the group above, life is easier. If it's surjective, yes. But notice, again, like a continuous open map, that is exactly saying U is open if and only if G is of U is open, if it's a bijection. Right, like that is basically that statement. Right, because like the pre-image of this being, right, like this G being equal to the pre-image under the inverse is where you like need the bijective part, but like that is showing that the inverse is continuous. And so yeah, like that condition on open sets for the quotient map is basically the thing that is forcing them both to be continuous. Continuous open map is quotient. So like not always. So again, it has to be surjective. An injective quotient is a homeomorphism. Well, no. So it has to be bijective in both. But yeah, bijective quotient map is a homeomorphism. Yeah. Yeah. Injective quotient map is a homeomorphism, yes. Yeah, it's essentially rephrasing that 203 in a lot of different ways and like seeing it through the lens of the definition of a quotient map. Right, because 203 is saying, geez, I turned it off. Right, F is a bijection, then F is a homeo if and only if the U, if and only if F of U, right, kind of thing. And so this part is basically, if you have a bijection, then this basically boils down to the open set condition for being a quotient map. But again, F has to be a bijection there because you need F inverse to actually exist to take the preimage of it and call that the same thing as the image of F. Right? So like that's where the bijection is very important because F is equal to F inverse inverse. So like that is key there. continuous map and an open map. I mean, one's talking about maps going forward, and the other one's talking about the pre-image, right? So like open map is about the image of open sets is open. The other one is pre-image of open sets is open. So that's the key difference. And again, like usually structure is preserved by pre-images in terms of open sets, but like not necessarily so with open sets. And so like that's usually the harder condition to check, is being an open map. Okay, so then 219, this is one where, yeah, I think you're not going to be able to show it's an open map. So this is a good example. So we have the relation, right? So again, everything is equivalent to itself, and then we just glue 0 to 1. And then we want a map to S1. We want to show that this is homeomorphic, right? So basically taking the interval, gluing these points, should get us a circle, so we should hope this is a homeomorphism. So to show it for real, we would need a map, right? So what map did you guys come up with from 0, 1 to S1? You had already seen one. So think about what points on the circle can be parameterized by. Yeah, so do you mean the cosine? Yeah, so. Yep. Right. So. Let's continue. Yeah. Okay, so. Right. And we already know that like this definitely didn't give us like a bijection from, you know, the half open interval from 0 to 1 to the circle, but that's fine. We're gluing both of these points together. So this should like eradicate that issue of having different stuff happen at the two endpoints, right? Because now they're just going to flow nicely because we're gluing them together. So those things that were suddenly far apart when they were near the point 1, 0 on the circle are now not going to be far apart because these things are actually close together when we glue 0 and 1. So we've kind of remedied that issue with this gluing. So let's see like why it works, right? So again, we have to check our condition. So when is this going to be true, right? So like g of x equals g of y if and only if cosine of 2 pi x equals cosine of 2 pi y and sine of 2 pi x equals sine of 2 pi y. And so this is where I saw some potential issues with using like arc cosine and arc sine by folding. Oh, sorry. Yeah, you're reading Mark's thing. Yeah, so the issue there is, again, thinking about the ranges of these inverse trig functions. So you're going to get things, especially with arc sine, right? So arc sine is another one that goes from negative pi over 2 to pi over 2. And so you would go, when you divide by 2 pi, from negative 1/4 to 1/4. So it's like a little bit weird there, but it is true if and only if x equals y or 2 pi x and 2 pi y differ by 2 pi, which happens if and only if x equals y or the absolute value of x minus y is 1, which basically happens if and only if x equals y, or you have the cases where x equals 0 and y equals 1, or x equals 1 and y equals 0. Well, that's fine. This is exactly how we defined our equivalence relation, right? You identify points that are the same, or if they're not the same, the only ones that we glue are 0 and 1. So we do get this condition. You have to be a little bit careful with just like canceling things willy-nilly with arc cosine, which makes sense, because like if you do arc cosine, you would just get like 2 pi x equals 2 pi y, but that doesn't have to be the case, right? They could differ by 2 pi. So then, again, we just have to show its quotient, right? So G is surjective, clearly. Cool, yeah, I mean, that is the parameterization of the circle, so we're going to get everything. We don't even have to include 1, right, to get that. And you showed that before. And in fact, you've already shown that G is continuous and, well, yeah, I mean, we know that G is continuous. So the real question is the pre-image issue, right? So if U is open in S1, then the pre-image of U is open in S1. This is something we've seen before. I mean, this is basically done before slash, I mean, it's cosine and sine. So like it's going to be continuous, right, as this product of continuous maps. Oh, sorry, yeah, yep. Thank you. So so like, yeah, I'll ask the question, is G open? So if you have an open set, is its image open in S1? No, it's not an if and only if statement with the open maps, so it doesn't have to be. No, so like the statement that's equivalent, no, G is quotient, yes, but being quotient is not the same as being a homeomorphism. So like what you were discussing after the last question, like that was more about like F and not G. But like F is quotient, yeah. Yeah, it's not entirely if and only if. It's like an injective quotient map. G is not injective. No, it doesn't have to be open. Again, this is because G is not bijective. No, so look back above. Boils down to it being a bijection. G is not a bijection. Because to talk about the pre-image under the inverse, you have to have an inverse exist. And so like being an open map, it suffices, but it is not necessary. All right. Yeah, sorry, Nick, what were you saying? Yeah, so this is where it's not always enough, right? So like it would be enough, but it's not always possible to show that G is an open map. So here we actually have to check G inverse of U open implies, or the preimage of U under G is open if and only if U, or sorry, we already know the one way, so implies U is open. And in this case, yeah, again, I think it helps to think via the contrapositive. If you have something that is, so again, where we open in 0, 1, this is open in S1. So if you have something that is not open in S1, it's going to have some closed endpoint, right? Then you'll have like some, at the very least, half closed arc kind of thing. And then its preimage is going to be, so then its preimage here will not be open. And 0, 1 as well. Right, so if you go back, mapping a half open, so again, if it's half open, like not intersecting this circle, so if we do half open here, right, then we're just going to map back to half open here. And then if you have, well, a half open including it is definitely an issue. So half open, time-wise, so right, if you have this, you're going to run into the same issue where I don't really even know where I'm starting, so if I go this way, then you're going to get like a closure here, and then like an open here. And then, wait, what goes wrong here? So, oh, right. Yeah, U is not open. Yep, exactly. So this would be like this and this guy. Yeah, there we go. So these are like our cases here, and so none of these are open in 0, 1. And thus it would be a quotient map. When just half closed stuff. I mean, the same issue happened, right? Like, I mean, why just half closed stuff? Because it suffices to look at that. So, I mean, right, if you added another closed part here, all you've done is make this more problematic, right? You would just go back and, like, close up all these things. So, like, it's also not open. The way I'm really think of it there is, like, if it's not open, there's some point in your set that's not in the interior. And then if you look at its preimage, it's still not going to be in the interior. Mm-hmm. What do you mean? Oh, like open on that specifically. Yeah, so I mean, if you don't include that, then you didn't include either. So I mean, really, it would just be the rest of where it is, right? So it would just be, like, this would be its preimage. Right, because you get rid of this issue. So, like, it doesn't matter that 0 is equal to 1 here. Any other questions on stuff? So I mean, yeah, it might be useful to try your own flowchart, but again, like, yeah, so G, surjective, continuous, and open implies quotient, but this isn't true. Strange world we live in, I suppose. Yeah. Because that condition on preimages of open sets is, like, ever so slightly different. And again, it really is that, like, G being equal to, right, like G of U equals the preimage under the inverse. Like, this doesn't make sense if you don't have one-to-oneness, right? So if the inverse doesn't exist, then this doesn't make sense. And so, like, that's the real issue there. But, like, this is true because G of the preimage, which always makes sense, right? We can talk about a preimage, is equal to U if G is surjective. So that's why, like, surjective gets you enough to say quotient if you have open, but if you're not injective, then you can't really go the other way. So in terms of, like, time, I don't know. I may write up something for 221, but I think, like, we should probably move on to metric spaces next time just to make sure we actually, like, cover some important things. We won't spend a lot of time on metric spaces, mostly because, like, a lot of that is more the world of analysis anyway, and a lot of it is, like, fairly intuitive, and you've already kind of seen a lot of the topics with just, like, R2 and R. So the main thing we're going to focus on there are separation properties, because those are some more like topological invariance, like properties that would be preserved under homeomorphisms. And so those are interesting ways to distinguish between spaces. All right. So that'll be kind of the focus. And yeah, you should watch Nick's Pi video because it's cool. And seriously relevant with 226 or whatever it is. Alrighty, have a delightful day.